At its most fundamental level, a server is not a specific physical object, but rather a role that a computer fulfills. It is any system or device dedicated to providing resources, data, services, or programs to other computers, known as clients, over a network. This client-server model forms the foundational architecture of nearly all modern networked computing, from checking email and loading a website to streaming a movie or accessing a shared company database. While any computer, including a standard desktop, can be configured to act as a server, the machines professionally designed and built for this purpose are engineered with a radically different philosophy than their desktop counterparts, prioritizing relentless reliability, massive simultaneous connectivity, and high-throughput data processing over user-friendly interactivity and cost-effectiveness. The core distinction begins with hardware architecture. Desktop computers are optimized for a single user to run a variety of tasks sequentially or with a limited number of foreground applications, featuring consumer-grade components like a single powerful CPU with a high clock speed for fast single-threaded performance, a graphics processing unit, GPU, geared towards rendering complex visuals for games or creative software, and a moderate amount of RAM sufficient for a responsive user experience. In stark contrast, a server is built as a multi-user, multi-application workhorse, often equipped with multiple physical processors, or CPUs with a high core count, that can handle hundreds or thousands of simultaneous requests, error-correcting code, ECC memory that can detect and correct data corruption in real time to prevent crashes, and hardware RAID, redundant array of independent disks, configurations that spread data across multiple hard drives for both performance and, crucially, redundancy, ensuring that a single drive failure does not result in data loss or service interruption. This hardware divergence is driven by the divergent missions of the two machine types. A desktop's primary mission is to provide an excellent, responsive experience for one person sitting in front of it. Its failure is an inconvenience affecting a single user. A server's mission is to provide continuous, uninterrupted service to potentially thousands of clients. Its failure can cripple a business, take a website offline for millions of visitors, or halt an entire company's operations. This imperative for uptime dictates every aspect of server design. Where a desktop typically sits in a quiet office, servers reside in climate-controlled data centers with redundant power supplies, often equipped with hot swappable components, meaning power supplies, fans, and hard drives can be replaced without shutting down the entire system. Their physical form factors reflect this need for density and manageability. Instead of the familiar tower case, servers are often mounted in standardized racks, appearing as sleek rectangular units, hence rack servers, that can be densely stacked to conserve space, or as even more modular blade servers that slide into a chassis sharing common power and cooling resources. The operating systems they run are different as well. While a desktop might use Windows 11 or Mac OS, servers typically run specialized, hardened operating systems like Windows Server, Red Hat Enterprise Linux, or Ubuntu Server, which are stripped of graphical frills to conserve resources and are configured for remote headless administration, meaning they are controlled entirely over the network without a directly attached monitor, keyboard, or mouse. The software that runs on servers is also fundamentally different from desktop applications. Server software, often called a service or daemon, runs in the background, silently listening for incoming requests on specific network ports. A web server like Apache or Nginx listens for HTTP requests on port 80 or 443. A file server using the SMB protocol listens for file access requests. A database server like MySQL or Microsoft SQL Server listens for queries to store or retrieve data. These services are designed to be stable and long-running, often operating for months or years without restarting. Desktop software, on the other hand, a word processor, a video game, a web browser, is inherently interactive and transient, launched and closed by a user as needed. The performance metrics that matter are also inverted. For a desktop, user-centric metrics like application launch time, frames per second in a game, and smooth UI scrolling are paramount. For a server, the critical metrics are throughput, how many requests can be processed per second, latency, how quickly it can respond to each request, and uptime, the percentage of time it is operational and accessible. A server can have a slower individual CPU core than a high-end desktop gaming PC, but will vastly outperform it in a real-world workload by leveraging its many cores to handle numerous tasks concurrently. This specialization extends to networking. A desktop typically has a single standard gigabit network interface, sufficient for browsing the internet and accessing remote files. A server will often have multiple high-speed network interfaces, 10 gigabit Ethernet or faster, that can be bonded together for increased bandwidth and failover, ensuring that if one network card fails, traffic is automatically rerouted through another without dropping the connection. The concept of scalability is another key differentiator. A desktop is a fixed entity. When it becomes too slow, you replace it. Servers are designed to be scaled, either vertically, scaling up, by adding more RAM, more CPUs, or faster storage to a single machine, or, more commonly in modern cloud architecture, horizontally, scaling out, by adding more server nodes to a cluster to distribute the load, a flexibility that is essential for handling variable demand, such as a retail website during the holiday season. This leads to the modern paradigm of virtualization, where a single physical server can be partitioned into multiple isolated virtual machines, each acting as a separate server with its own operating system and applications, a concept that is the bedrock of cloud computing, where services like Amazon Web Services or Microsoft Azure are essentially providing access to vast farms of such virtualized servers. In summary, while both desktops and servers are built from the same fundamental components, CPUs, memory, storage, and network interfaces, their design philosophies, hardware selection, software ecosystems, and operational requirements are worlds apart. A desktop is a general-purpose tool for an individual, optimized for a rich, interactive experience and a tolerable cost-to-performance ratio. A server is a specialized engine for delivering services, optimized for unwavering reliability, massive parallel processing, and remote manageability, with cost being secondary to mission-critical durability and performance. Understanding this distinction is key to comprehending the invisible infrastructure that powers our digital world. Every time you send a message, load an app, or save a file to the cloud, you are interacting with these silent, powerful workhorses operating in data centers around the globe, performing their dedicated roles with a level of endurance and specialization that your desktop was never designed to match.